And go.
Welcome everybody. My name is Seung. First, I would like to thank the organizers, especially Professor Cholho Choi and Michael, for inviting me to this very nice event. Today, I'm going to talk about PyUnixMD, a Python-based excited state molecular dynamics simulation package developed by our group, and it has multiple features, especially it can handle the decoherence phenomena based on the eject vectorization. So, the outline of my talk is following. First, I will briefly introduce the role of excited states in molecular systems, and I will introduce the electron-nuclear correlation from eject vectorization of full molecular wave function. And then I will introduce the mixed quantum classical approach beyond non-adiabatic couplings. Then I will introduce the features of the PyUnixMD program, and I will summarize my talk. So excited state plays an important role in molecular systems. For example, we have an electron transfer phenomena in photovoltaic cells, and also we have exciton transfers in photosynthesis. Also, we have very special phenomena, which is called thermally activated delayed fluorescence, which is aiming for the development of display devices. Also, we have a nanoscale transport phenomena, which is related to the polaron transport. So actually, everything is about the coupled electron-nuclear system or correlated electron-nuclear system, which is quantum mechanical. So in principle, we actually deal with this entire system quantum mechanically by solving this full quantum dynamics by using this time-dependent Schrödinger equation or quantum Liouville equation and so on. However, as we all know, we cannot solve the entire system quantum mechanically. So one way to solve this problem is called mixed quantum classical approach. So in this mixed quantum classical approach, we actually consider the system, quantum mechanical system, which contains electron or excitons, which has quantum mechanical features, and the remaining part as classical mass, such as nuclei. And then we consider the interactions between this quantum system and classical mass. So this is called mixed quantum classical approach. And this mixed quantum classical approach is very useful when you consider the excited state molecular dynamics, which has a non-adiabatic phenomena. So when you consider the nuclear dynamics with the excited state, then we have several key ingredients. So when we understand the dynamics here, then actually we need first the multiple von Oppenheimer potential energy surfaces, which actually give the potential for the dynamics of nuclei. And then based on these potential energy surfaces, we actually simulate quantum mechanical feature of nuclear dynamics, such as nuclear wave packet splittings. So depending on the potential energy surfaces, nuclear motion has different behaviors. So we have kind of branching phenomena. And then actually there is a non-adiabatic electronic transition, such as internal conversion or intersystem crossings. Then we have population exchange due to this non-adiabatic phenomena. So these are usual ingredients to understand the nuclear dynamics with electronic excited state. So there are many possible ways to handle this problem, such as Ehrenfest dynamics or surface hopping dynamics. However, these approaches have quite critical problem, which is called overcoherence problem, which keeps the electron wave function always in coherent state after non-adiabatic crossing. So this is quite crucial for the long-time simulation of this mixed quantum classical dynamics. Thus, we need another approach by keeping this mixed quantum classical concept. So back to 2010, actually, we developed a new approach, which is called eject vectorization. So this eject vectorization starts from writing down the entire molecular wave function as a single product between this nuclear wave function chi and electronic wave function phi here. So here the total molecular wave function psi is the solution of the full molecular time-dependent Schrödinger equation. And here the electronic wave function phi satisfies the partial normalization condition. So if we integrate out the probability density of this phi for any nuclear degree of freedom, then actually it always gives 1. Okay, this is the partial normalization condition and it is enforced. So in this case, the nuclear wave function chi actually gives the exact time-dependent nuclear density, and the electron wave function phi gives a time-dependent, a single time-dependent potential energy surface, and a single time-dependent vector potential A, which can be written like in these equations. So the overall equation of motion for nuclear wave function can be written like this way. We have a Schrödinger equation in the presence of the vector potential, time-dependent vector potential, and time-dependent potential energy surface. And then we can also derive the equation of motion for electronic wave function, which can be written like this way. So we have the Born-Oppenheimer Hamiltonian, and we have electron-nuclear coupling operator or electron-nuclear correlation operator, and we have a scalar potential epsilon there. Then this electron-nuclear correlation operator can be written like this way. So we have very, very complicated and weird form here. And we can say this is the exact shape of the electron-nuclear correlation. So compared to the well-known NFS dynamics, we have additional part from this eject vectorization, which is the electron-nuclear correlation operator here. So if you look at this electron-nuclear correlation operator, so we have two terms. So the first part is this term. So we have this term here, and actually this term gives a potential corresponding to the diagonal Born-Oppenheimer correction, the debug term. So in other words, if we calculate the expectation value of this term with this electronic wave function as a function of this nuclear coordinate, then this term gives the diagonal Born-Oppenheimer correction term when the electron wave function is in an adiabatic state. Actually, the important part is the second term. So if you look at this guy here, then this guy actually can be written as this term. So if you consider the phase of the nuclear wave function, then this phase term with this vector potential gives the classical canonical nuclear momentum, and the marginal part of the nuclear wave function here, we have this guy here, which is called quantum momentum. So we have classical momentum part and quantum momentum part here. Then this classical momentum actually provides the Ehrenfest equation with trajectories. So we have coupling of this classical momentum and this derivative, okay? And also the quantum momentum provides the additional correlation between this electron nuclei, and it is beyond non-adiabatic coupling, and actually it can generate quantum decoherence phenomena. So this is very important here. So by using this eject vectorization, okay, we can actually derive the correct electron-nuclear correlation here. Then this correct electron-nuclear correlation contains classical momentum part here and quantum momentum part, which depends on the shape of entire nuclear wave packet. Okay, so this quantum momentum part can generate the quantum decoherence phenomena, which we will show you later. And based on this formula, the eject vectorization can capture the correct behavior in potential energy surfaces. So if we consider these two adiabatic potential energy surfaces here, epsilon n and epsilon m here, then if you consider the nuclear dynamics starting from the upper state, okay, then we have non-adiabatic coupling region here. Then the effective potential energy for nuclei as a function of time looks like this. For Ehrenfest dynamics, we have what? The mean field potential energy, because electron wave function is in coherent state. So we cannot capture the nuclear wave packet splitting by using this Ehrenfest dynamics in general. So to avoid the problem of this Ehrenfest dynamics, surface hopping dynamics, we actually consider the effective potential as either one of these surfaces. So we can actually have this surface or this surface and this surface. Okay, so this is the effective potential of trajectory surface hopping dynamics. And actually, if you consider the exact potential energy, then actually it looks like this. So after the non-adiabatic coupling, we have a coherent state. And then if you consider the nuclear wave packet along this lower state, then actually it naturally follows the lower state. So this is the exact surface actually, which can be obtained from this equation. So if you consider the average nuclear configuration like this way, where the chi n is the nuclear wave packet on nth adiabatic state, then the potential from this eject vectorization actually generates this kind of behavior. To see a possibility to mix quantum classical approach based on the eject vectorization, we compare nuclear dynamics of full quantum simulations and trajectories on the exact surfaces. Here, trajectories on exact potentials follow the gradient of the potential, and we plot the histogram of the trajectory positions. So after a single avoided crossing, we can see the nuclear wave packet splitting from the quantum dynamics simulations here. And surprisingly, we can also see the splitting of trajectories from the classical dynamics according to the Newtonian equation. Therefore, if we handle the correct potentials, classical trajectories can capture the correct nuclear wave packet splitting. Thus, we can move on to develop an algorithm for mixed quantum classical approach based on the eject vectorization. Actually, I don't want to explain all details of equation motion from the eject vectorization approach, but one can derive coupled equation motion based on the previous electron-nuclear correlation operator with a suitable choice of gauge. The electron equation motion can be written as this equation, and here, as you can see, the black equation actually corresponds to the atom phase dynamics, and we have an additional term which is in orange color, and this one contains the quantum momentum here. And also for nuclear equation motion, we can have the same analog like this way. So this black equation corresponds to the atom fast force, and we have additional orange color equation, and this one corresponds to the what? The quantum momentum. So we have quantum momentum here, and we have quantum momentum here. So these additional terms are called the coherence term, and when we consider a purely classical nuclear motion without quantum momentum, then we can say that these coupled equations becomes atom phase dynamics. So as you can see in these equations, to compute this decoherence term, we have to calculate the quantum momentum here and the special derivatives of the electronic wave function with respect to the nuclear coordinates. So this is the difficulty to evaluate this term actually. And we can obtain a simplified version of this equation of motion when we consider the Von-Traun expansion like this, and the special derivatives with respect to the nuclear degree of freedom for this electronic wave function becomes a derivative of phase term, which is approximated as this equation. This is the time integral of this Born-Oppenheimer force. So this is kind of impact in classical mechanics. And also one can prove that the decoherence term becomes zero if we have a decoherent state. In other words, when the electronic state becomes an adiabatic state, then this term becomes zero. So these equations are reduced to the typical Born-Oppenheimer dynamics for decoherent state. So to exploit these previous coupled equations, actually we need additional ingredients compared to the atom fast or surface hopping dynamics. First, we need positions of all trajectories to construct a nuclear quantum momentum. So initially, we have a distribution of nuclear trajectories, and it evolves in time. And each time, we put Gaussians on each trajectories and construct a nuclear wave packet or nuclear density, overall nuclear density like this way, and we calculate the quantum momentum at each trajectories. And after some time evolution, we have another step, another time step here. Then also here, we calculate the quantum momentum from the coupled trajectories. So in this construction of quantum momentum, the trajectories are talking with each other. So this is coupled trajectory approach. And also we need the phase vectors from all Born-Oppenheimer forces. So we have to calculate this vector here to evaluate the decoherence term. So these two terms are the main part of our mixed quantum classical approach. And in addition, we have to note that all trajectories should be run simultaneously to construct quantum momentum at each time step. And actually, we developed this kind of algorithm and applied this algorithm to a simple model system, like the one-dimensional symmetry system. And we can actually obtain very nice results for this system, like this way. So we can describe the correct potential energy surfaces and correct distribution of the nuclear density So we can see the splitting of nuclear wave package, and also we can see the correct spatial distribution of the coefficients or Born-Oppenheim populations. So we can see this kind of spatial crossing of the Born-Oppenheim population when the nuclear wave packet splits. Moreover, we can describe the decoherence, the electronic decoherence phenomena in this dynamics. In this case, the decoherence means the decay of octagonal element of electronic density matrix. So when this nuclear wave packet crosses the non-adiabatic coupling region or over the crossing region, we can see the increase of the coherence pattern. And after that, when nuclear packet splits, then we can see the decrease of this coherence pattern. So we can see the increase of coherence and decrease of coherence. So this green part is the quantum mechanical result, and this pink line is for our CT-MQC method. And here, as you can see, in atom phase dynamics, there is no decoherence because we